doesn't happen again. The inspiration for this is that a lot of reinforcement learning algorithms, as I was getting into them and learning how they work under the hood, you start noticing that we might have 10 algorithms that have different names and different purposes, but as you start learning how they work under the hood, they turned out to be surprisingly similar. They might differ to a couple of hyperparameter changes. So that's what I want to talk about today. Let's start with the very basics. We'll skip them quite fast, but it's important that we're all on the same page. So what exactly are we talking about today? We are talking about the reinforcement learning in partially observable Markov decision process scenario. So it's a scenario where you have to develop an agent, you have to develop an algorithm for an agent that sends an action. Is Mateusz the only one who can hear me? An agent that, say, okay. And some people do. Well, let's figure this. What about everyone else then? I mean, I guess I'll continue if it's only a couple of people. It's probably on this side. So it seems like the majority of other people can hear me, and you just dropped in at the very right moment when I'm introducing the partially observable Markov decision process. It's a scenario where you develop the agent that sends these action messages, these A's, to the environment, and the environment responds with an observation and a reward. The observation is just some information about what happens, and the reward is a number that tells you how good you're doing. I really like this picture because it really highlights the symmetry of it all. Because an environment is also an agent in some sense, and if you look at it from the perspective of the environment, your actions are the environment's observations, and observations are the environment's actions. And there are a lot of scenarios where we can choose what's the environment and what's the agent. So in healthcare setting, for example, we can model interactions between the doctor and the patient's body. And in different use cases, we will model a doctor as an agent, and we will try to train optimal treatment algorithm that will lead to patient behaving better. In another scenario, we will model a patient as an agent and a doctor as an environment, and we'll try to make a precise patient model. So this is what we are going to talk about. What we're not going to talk about is the stuff in the left and in the right part of that slide. So the reinforcement learning takes place in between more general and less general approaches. The approach you take in machine learning depends always on what data you have available to you. Right, this determines everything. If you have absolutely no data, you just have some function, some test, and you are trying to optimize it. So you're trying to find inputs to that function such that this function returns a high number. This is the black box optimization. Hopefully you recognize our good friend, the black box here, and you can treat reinforcement learning as a black box optimization, right? You need some agent that does well. You generate this agent, you represent it with a neural network or something, see how well it does, test it, get a result, try again. But in reinforcement learning, you do have some more information, right? You have this step-by-step rollout. You get rewards and observations at every step. And so it lets you be a little smarter than just black box optimization. Then there are scenarios where you have more information, and then you might use different methods. For example, if you have a reference agent, if you have a human, for example, who did the job that your agent now has to do, you can use imitation learning. You can try to start with replicating what this agent, human, does, but that's going to be our boring supervised learning, right? right? There's going to be behavior cloning. And then if you know something about the internals of the environment, of how to behave, and good examples of that are games like chess and Go. Because in games like chess and Go, the environment is the game and your opponent. And you don't know the internals of your opponent, but you do know the rules of the game. And so you do know a lot of stuff about what can and what can't happen. So you have a lot of additional information that you use. So we're not talking about the scenarios, we're talking about purely POMDP frameworks. A lot of interesting stuff gets left behind. Other things we're not talking about is different implementation details and especially proofs. Proofs are the hardest, the longest, and the most rigorous part of reinforcement learning. And that definitely doesn't let you fit even like a couple of algorithms in one lecture, not all of them, which is what I tried to do today. Right, so if you were the kind of person who wants to learn things rigorously and wants to learn all the proofs, you'll probably, faced with a partially observable Markov decision process task, you'll probably go grab a textbook. But if you're of a more practical mindset, you probably head to GitHub and look at software that solves this exact problem. These libraries are sorted mainly by GitHub stars, except this one, Autonomous Learning Library. It has just 50. There's just 500 stars, which is very low, but one of them is mine, so it has to be on that slide. And what you'll see if you look at these libraries is this big list of algorithm names. At the environment, the library will just tell you that choose which of these you want to use. And obviously you do know which one of these you want to use, right? There's no way you don't. And at first glance, it can be really daunting. Our goal today is to make it a lot less daunting. So the required background here is that we know how to learn functions from data. Our old basic supervised learning, right? If the domain, if we have a function and we don't know the function, but we know some examples of inputs and outputs. If the function is defined over a discrete domain, then it's just a table. Where right there are there's a finite number of possible inputs, so we can take the average of the outputs for every input and say that that's going to be our predicted output, basically. And if it's defined over a continuous domain, our main approach to that, and there is a theorem which probably a lot of people know about that proves that our neural networks are like universal function approximators. That they can, given enough nodes, they can approximate any function. So over a continuous domain, our tool of choice is neural networks. That's what we know how to do, and we want to leverage this in a more complex, in a reinforcement learning setting, where we have this additional complexity that we're not just learning from a data set, we're actually gathering the data set as we go, because we have to interact with the environment to gather this data set. Now, the first trick is something that's also familiar to everyone outside of reinforcement learning. It's what we do when we need discrete outputs. So the discrete outputs are the one that our traditional approaches don't handle very well, because of all the averaging we do, right? The outputs are always become real valued and right, and complex. So what do we do usually when we need the discrete outputs in any neural network? When we, for example, in a classification task, right, we need to get a discrete output from a neural network. And what we do there usually is probabilities. Right? We replace an idea of a function that outputs a discrete number with a function that outputs several probabilities for every option that exists. And the same thing happens in reinforcement learning. So there are two, if your action space is discrete, if your action space is continuous, then usually in reinforcement learning, what we do is we learn this a of s function. So the function of action from observation. But if it has to be discrete, if it has to be one of the options, we learn the policy, which is a distribution of probabilities. Right, so that's like trick number 0, because it really comes out from outside reinforcement learning. And with this trick, we can already implement our like number 1 algorithm, from which like everything else stems from this like tree. It's called reinforce algorithm. And what it comes down to is that we want to take an action that maximizes the future rewards, all of the future rewards in the episode. And now there is a simple way to do it and a more complex way to do it. A simple way to do it is to just sum them up. So if I play a chess game with like 1,000 moves, for example, we have 1,000 move limits, let's say that we have such. Then my goal is to maximize the sum of all rewards, to take an action such that the sum of all rewards after this action will be maximized. Because actions can have consequences long in the future, right? It's very wrong to only look at the first reward that comes. Now, a more complex approach to that would be to use a discounted sum of rewards, where we sum up all the rewards, but each next reward has a slightly lower weight. Because rewards now are more useful than rewards later. In finance, it's usually because you can reinvest rewards now. In reinforcement learning, it really has to do with, well, one, if your environment doesn't have an end. If it's an infinite environment, you have to discount. Otherwise, you can just never get rewards and believe that you will have a bright future sometime. But also, it helps with attribution because it's quite hard to tell which action led to which reward, and it is more likely that an immediately preceding action is the one that led you to reward. Not always. Sometimes you do something in the very beginning of the game that helps you in the end, but it's more likely than the immediately preceding action is the important one, the one that led you to the reward. So what we do in a reinforced algorithm is we run an episode. We don't update we have a policy model. So we have a neural network that represents this policy function. We run an episode playing the game with this policy. We don't update it during the game. We run a whole episode, and in the end, for every action, we can calculate this magic number, the discounted sums of all the rewards that came after this action. And then it becomes, after that becomes just like supervised learning, where you have a data set of actions and scores, where the score is this discounted sum of future rewards. And you need to learn a function of which actions give you high scores. So your loss function is the probability of the action by its score, minus probability of the action by its score. And this is the algorithm the bedrock algorithm. Now, everything else, I claim, let's see if I can convince everyone of this, is like a bunch of tricks that can be applied on top of this to make it work a little better. Now, let's go through, if you don't have any questions at this point, by the way, feel free to jump in. Let's talk about these tricks. Right. One trick is to model at a different level. Instead of directly learning this policy function that outputs actions, take a look at these Q and V functions. So they have a definition. The Q function is a function that tells you how good a certain action is in a certain state. Right, so you observed state S, and Q of state S and A is the function that tells you how valuable it is to take this action in this state. And the V function is a state value function. It just tells you how valuable a certain state is. there are certain states, for example, think chess, right? In chess, there can be a state where you don't really have any good moves. You're gonna lose like in a couple of turns anyway. Alternatively, like also there are states that are very good, that are, you probably can screw them up, but you have a lot of good opportunities from that state. And they have a formal definition under a certain policy. Like the value of a certain action can be defined as an expectation of this score. Basically, it's the expected score. So we already decided that score is the discounted sum of future rewards, right? And the quality of an action is the expected score after this action. And the quality of a state is the expected score after this state. Now, expectation is a little tricky in machine learning, right? How do you code expectation? But you can just say that if you are using an on-policy algorithm, which means that you are exploring the environment with the same algorithm that you're training. So you have this p function, pi function, and you use it to take a step, and then you learn, you take a step in updating it. You take another step with p and you update it. Then it means that the average, if you just average the scores that you've collected, right? If you just average the scores that you've collected over your game, you can say that this approximates the expectation because it's just a sample, right? If you average the scores that you've collected, it is a sample of that value you're trying to find the expected value of. So you can think of it as an approximation of the expectation. And this is how you can learn these functions. Now, what is the advantage of all of this, right? It was so simple with the policy function. Why should we train Q neural networks or V neural networks instead of the pi neural networks? And one big advantage is that you have some choice over how to translate Q into action. On the one hand, it's very easy to translate Q into action. So if you are in a certain state, and you can say what the value is of every action out of this state, it's pretty easy to make a decision, right? You just pick the best. But there is some, there are some options here. For example, you can decide that you will be picking them stochastically. And instead of just picking the best action all the time, this option, will pick some distribution over the actions. That's somehow the higher the Q, the higher the probability of taking action. Or you can take this epsilon greedy approach, which essentially means you flip a coin, or like a coin is always 50-50. You flip an epsilon coin that can have skewed probabilities. And if you get one side, you pick random action. And if you have another side, you pick the best action. What this helps you do is it helps you explore. It means that you don't. It means that you don't come to a local minimum very fast. So if you don't explore, and if you always do what you think is best, you might have tried two options. One worked out, the second didn't work out. And you then live the rest of your life in fear of doing one, and in trying to do two. And you just repeat these two, even if there are better options, you just didn't encounter them yet. So it's good to add some randomness to pi, just to make sure that you keep exploring the parts of the environment that you haven't seen yet. So a practical example of this. This is my morning commute to work, and I pretty much use reinforcement learning to find the fastest way. I have a big motivation to cycle very fast because the time it takes from my home to here is just around half an hour. So because I use Believe and I have only half an hour free, how fast I cycle really determines whether I get to pay extra or not. This morning, so I really had to learn what is the fastest ways from there to here. And in the beginning, I pretty much was using the absolute greedy policy. You flip a coin in the morning, and if it's one side, you're doing a new random route. And if it's another side, you're going the route that you think is good. And yeah, I initialized it with Google Maps, but that turned out to be quite bad, so some learning was required. But like for the last 20 days, for the last 10 days, I haven't paid for it ever, so I think it works out. And this is one of the big reasons to model Q instead of modeling pi, because it lets you choose your approach to actions between these options, between the stochastic option, the always maximum option, the epsilon greedy option, and it lets you one of the options for exploration. So what I used for the first days, and another option for actually applying the algorithm where you no longer have to learn. Now, these functions can be derived from each other, which is why you will never see an algorithm that models, for example, Q and pi with two separate neural networks, because pi is trivially inferable from Q. Right? If you have values for all the actions, you pick epsilon greedy policy, or you pick the best, and you get your pi basically. And if you have Q and pi, you can plug it in directly into the formula for the value, and you get the value function. Which also means that if you have a model for Q and pi, you don't need really to model V additionally. But some of these relationships are, some of the inferences are complex. So if you are in the continuous environment and you're trying to learn a deterministic action function, then it is directly inferable from Q. It's the A function is just the argmax of Q, is just the action that maximizes Q at this state. But Q can be a very complex function, and finding its maximum is a whole separate hard optimization task. So there you would see actor-critic methods which model both of these functions, so that you don't have to make difficult calculations of A from Q. So you can think of, you can already directly classify all the algorithms into which of this they choose to model, basically, which of this they choose to learn, and which of this they derive. So I showed. Now another trick we can apply is, remember, as I said, in reinforced algorithm, we didn't do any updates during the episode. We waited until the end to update the policy. And that's because making updates on the go is fairly tricky, because your score is the sum of all future rewards. And you don't have all future rewards unless you finish the episode. One trick that lets you get around that is to make the function depend on itself. So you can say that you have this wrong value function. You know that it's not perfect, and you've just gotten a reward that sort of tells you how good or bad it is. But you can use it to sort of bootstrap, to sort of approximate your discounted sum of future rewards. So you do something, you get a reward, and then you can say that, and then by our definition, right, the Q, the value of this action is the expected sum of future rewards afterwards. So it's the reward you got, which you know, plus the sum of all future rewards, which you don't know. But the sum is valued by your model. Your current model is actually trying to approximate that. So you can, in learning this function, use itself. You say that the reward plus the value of your function's estimate of the value that you will get into is your new expectation of the value of the current state. You can think, I think it's very useful to think of a particular environment. For example, in chess, there is a lot of work done to just model this value function separately. They actually don't, they often have like a game-specific value function, which isn't trained, but instead they just have like chess experts work out what is the value of a certain position. And so in chess, the value of a move is the reward you get after this move, plus your expectation of the value of the next position. And you can use it to update your expectation of the current position based on your expectation of the next position. And so this TD objective, time difference objective, this trick lets you do updates at every step. And this really speeds up learning because you essentially you explore much faster. Your policy is getting better during the episode. You're not waiting for the end of the episodes. And there's one bright example that's always used. That's sometimes it takes like if your episode is n steps long and you only get the reward at the very end, and you don't use time difference objective, then it will take you n episodes to actually learn what to do in the beginning. Because what you have to do in the beginning is to improve your chances at the second step. What you have to do at the second step is improve your chances of the third step. But like at the beginning, you will only get the reward in the end, if that's the kind of the game you're playing. But only in the end you learn whether you won or lost. And you only can learn of what to do at the last step. Then you restart the whole episode, and you can learn what you can do in the second to last step. You restart the episode again, and you learn what you have to do at the third to last step. And TD objective fixes that. With TD objective, you actually learn like really, really fast. And finally, a trick that's also, I think, quite obvious to people from outside RHEL, if you model two of these functions. So what people often do is they model Q and V. You can determine V from Q and P, Q and pi, but the pi is actually depends. The fact that pi depends on Q sort of breaks it. So you can model Q and V, or you can model Q and A, because it's quite hard to get from Q to A. And when people do this, when people model two functions, you can share some of the neural network weights between them. Right? You can make essentially like three neural networks. One is some representer, some embedder of the current state, and then another will be for Q and another for V. All right, and now pretty much the rest of the field is about stabilization. The problem with everything we're doing now is that we are training based on some sort of approximation of this expectation. And this approximation is really, really noisy. Imagine you're learning to play poker, and you played the most terrible cards imaginable and won because everyone else had even worse cards. Now you're estimating the value of those cards you play as very high because in your experience, on average, it has been very high. And it will completely nudge you into the wrong direction. If in all of these reinforcement learning approaches, you keep the training is very noisy. If you plot, I should have included the plot. Sorry, if you plot this function, it will be jumping up and down like in very different direction all the time. It should over the long term average out, but this noise creates a lot of problem. You may jump inside. Might jump sideways and then get stuck in some local minimum over there. So a lot of reinforcement learning about how to stabilize it, at least a little bit, how to deal with this level of noise. And for that, there are a number of tricks. For example, you can always just clip your loss. You can set limits for how much you will be updating your policy or your value function, and update no higher than that. And this is something that this genius clipping formula is the basis for a very highly cited OpenAI paper. It was one of the breakthroughs in reinforcement learning. So yeah, and the trust regions. Some people will disagree with me, but I think that trust regions are basically fancy clipping. It's more like mathematically sound and trainable clipping. In trust region approach, you also clip all of your losses, but you have this trust regions that you use to clip it. So if it's in the trust region, you propagate it. If it's outside, you clip it to the next legal value. And this trust region can be also learned and updated. And this sort of solves a lot of big problems with standard clipping, because the standard clipping, choosing the coefficient is a big deal. It's a very important hyperparameter decision that's hard to make, actually. In a lot of scenarios, you sometimes have to hyperopt to try different hyperparameters. And trust region approaches go a long way towards making this better. Right. Then another trick that we use is optimizing for advantage instead of for Q. So if you train in the Q function, you have to take the action that's has maximum value, and if you take a high value action, you are highly rewarded and you learn to take this action more often. If you take a low value action, you do the opposite. But if you're in a very good situation, and pretty much anything you do will lead you to high rewards, then you will get high reward for anything you do, even if it's the worst possible choice. Right? If you got to such a good position that any choice will give you a high reward, but you're making the wrong choice, you still your loss is still good. And you have the opposite. Like if you're in a terrible state where you have no good options, it's still useful to pick the least bad option, but you will be negatively rewarded for that. And so it's instead of optimizing the Q, it's good to optimize the advantage, which is the difference between Q and expected Q in this state, because the value of a state is the average expected Q of all actions that you have out of the state. So that's trick 5. Now there is, I'm just introducing this quickly because it is in the basis of some algorithms. The advantage function can be just represented as this difference, but there's also an approach where they are limiting what the Q and V function can be to using this formula. So it has to always adhere to this formula because this makes the advantage function differentiable, easily differentiable, and easily optimizable, and it helps you solve this very problem. So if your Q function is easily differentiable and easily optimizable, then you don't have to think about how to model both Q and A. So you can have an environment with a continuous action space. You can train a Q function for that. And if it's easy to find the maximum of, then you don't have to train a separate action network. You just find the maximum of it. Right. Then Alexander asking about having trust region approaches and then clipping it. No, I don't think people do that often. People usually do either one of the two. People either use a trust region or clip it. Yeah, I would say there are just like two ways to clip something. Right. Then that's a trick that's also, by the way, can be very useful outside of reinforcement learning. We just don't have such noisy estimators in a lot of places outside of reinforcement learning. Is using a delay between function. So instead of, if you're training a Q function, for example, so which would be the critic network or like a V function, then it will be jumping up and down a lot. But what you can do is you can make a lagging twin of this function, which will be, for example, something like exponential moving average of your main function. There are different ways to implement this. You can basically at every step you train one queue, and then you make the other queue some average of its current value and the current queue, which is essentially means that your second neural network becomes an exponential moving average of your main neural network. And then you have this EMA neural network that's a lot more stable. And then, for example, for decision making, you can use that. So if you are doing on-policy learning, you make a step in the environment, and then you update your Q function. Then you can use the exponential moving average for taking a step, but you will keep your Q as your actual real Q estimate. And it will at least mean that all of the noisy changes in Q will not change your exploration strategy too harshly. Now, right, there are less than 10 tricks, actually, so we're getting towards the end of it. Now, trick number 7 is applying regularization just explicitly. You can also, from outside of reinforcement learning, you probably know that you can add some regularizer to your loss function. And in reinforcement learning, it usually takes the form of a maximum entropy regularization. So if you have a pi function that tells you what the probabilities of the actions are, it's probably better to be unsure about the action than sure if the reward is the same. Right? So if you have two strategies that yield the same reward, but one of them is really sure about what to do, and another has a lot of randomness to it, then the second one will explore much better. It has a much higher chance to morph into a better strategy in the future because it will explore more different state of the environments. That's one side of it, right? The very practical, what will happen? What will happen is that it will explore much more. But there's also like the theoretical reason that, you know, if a random strategy works, then the non-random strategy is definitely wrong, right? If a random model is good at modeling the world, and you have some very non-random model, your non-random model is probably wrong. So there are probably a lot of other strategies that are also good, and you just picked one of them and decided that that's the holy grail when it's not true. So it has this nice like theoretical property that's how reasoning actually works, right? But also it has this very practical advantage that it maximizes exploration. And then one of the most advanced tricks you can use is distributional reinforcement learning. Now we had a whole seminar on distributional reinforcement learning. I'm not going into any of the formulas or how that works, but essentially you take the approaches that now and you replace the Q and V functions. You replace the value functions with probability distributions. So you say that the value of a certain state is also stochastic. And it's some sort of probability distribution, and we just have to learn that distribution. It's also a super useful regularization, right? It prevents you from getting overly confident, and it makes you explore more. It's also a lot more true and helps capture, for example, actions that don't change anything, or like sometimes some states are really actually very random states, right? After that state, either something very good can happen or something bad, or they are high variance states and low variance states. In a non-distributional approach, you would treat high variance state and low variance state the same, right? You would assign them a zero value, for example, if it's a variance with a mean of zero, but one of them can have a variance from like dying to winning the game, and another is always always yields nothing, always yields zero. In healthcare, some experimental treatment will be a high variance solution, and it might have the same expectation as a known low variance solution. But this high variance is very important. It's very important to capture. And so distributional RL methods really try to achieve that and capture this directly. And there are three main approaches to actually modeling these distributions. So you can decide that this is the Q and V distribution or some particular distribution like a Gaussian, right, or something else. And then you'll be just learning the parameters of the distribution. And you can use a reparameterization trick, and you can backpropagate through that. And there are also approaches with piecewise functions and quantiles, where basically break the action in state space, the domain of the distribution into pieces, into segments, and measure how often these segments occurred, and count like the statistics and model a distribution in a piecewise fashion based on this. Right, and have two aids, so actually there are 10 of them, embedded counting. The aid trick is using, it's usually this particular method, Kronecker factored approximate curvature, but I would say it's just using any second derivative optimization approach. Any second level optimization algorithm. So this formula is the Newton's formula on how to find the minimum of a function if you know not just the first derivative but also the second. And if you know the second derivative, you can converge a lot faster. Like in this example, you'll take a much more direct route. Basically, knowing the second derivative lets you take a more direct route to destination. Essentially, our typical gradient descent algorithm is an approximation of a Taylor series, where you use all of the derivatives to make the step in precisely right direction. But because you only know the first derivative, you just use that and use it as an approximation. If you know the second derivative, you have a much better approximation and you can converge a lot faster. The problem is we actually don't. In none of the deep learning libraries that we use can calculate the second derivative normally. They calculate the first one and call it day. But we can use the history, just the history of first derivatives, to approximate what the second derivative is, and use that to make less optimization steps. And this might be more important in reinforcement learning than in other fields, because in reinforcement learning, we might be very step constrained. The environment might be costly to explore, especially if you're working with an environment that's an actual environment. Most environments are simulators or games, computer games that you have to win, and so on. But people also train robots with reinforcement learning in real life. Like you attach a reinforcement learning algorithm to a real robot, you give the algorithm a negative reward when it falls, and the positive rewards when it grabs the object you need, and you start learning, and the robot is doing random things and learning on the go. And in this sort of environments, steps are very expensive, and making the most out of the few steps that you have becomes very important. Now, the last trick, finally, is experience replay. It's the simplest one and one of the best ones, and most algorithms do use it. It just means that when you make an update step, so you've made a step in the environment, you got new information, you got your observation reward. But instead of just updating on this observation and reward, you update on a batch where you have the current information and a sample of older information. And this stabilizes you, because the whole reason why these algorithms aren't stable and jump around, because our goal is to make steps on the expected reward, right? But we only make steps on the last reward we got, and we use it as a high noise sample. So if you sample something from the past, you have a much lower noise sample. So this is a very easy to implement and basic way to do it. But the downside is that it's easy to implement, but it's just trading computation for stability. Right? If you have a big buffer, if you have a huge buffer, you first of all just got 20 times more computation. For example, if you sample 20 data points from history, and also you might actually develop slower, because now the new information you get is only responsible for 1/20th or 1/21st of your update. So it will get more stable. The probability of getting to local minima and other problems will be much lower, but you will have slower steps and more steps maybe to reach your destination. Right, and this is what we call the money shot in the industry. This is the slide the whole presentation was created for, basically. This is a slide where I claim that things that we usually call reinforcement learning algorithms are really hyperparameter sets, right? So on the here on the horizontal axis, you see the tricks that we've discussed. And now if you turn on and off some of those tricks, you make some combination of them, chances are this combination of tricks will have a name and will be called a reinforcement learning algorithm. I'll make this table available together with links to implementations of all these algorithms. So I would encourage people thinking about reinforcement learning algorithms not as proximal policy optimization, which is policy gradient with clipping, or R2D2, which is distributed version of DQN, which is just training a Q function with a TD goal, but as some combination of these tricks, and you just need to decide which ones are useful to you and which ones aren't, and implement that combination, or get an implementation of it, and think about really about whether you need clipping or don't, whether you need experience replay or don't. And so on, and instead of thinking about IQN versus NEC, which are abbreviations no one remembers anyway. So this is what I wanted to tell you today. I hope we have half an hour scheduled for discussion. I don't know if anyone has tons of comments and remarks and questions and ideas. But yeah. My favorite here is an algorithm called Rainbow, which tries to do it all. It basically tries to apply as many tricks as possible. And their paper is literally named combining the advances in reinforcement learning. And they just try to implement all of them together. And also, fun fact, around half of these papers, each of these algorithms has a paper, of course. And about half of these papers have Sergey Levin as a co-author, and we have a certain Sergey Hal constantly lurking in our seminars. So if it's him, it's kind of awkward. Please correct anything I said wrong about your algorithms. Right. Any questions, comments, remarks? Alexander, type in something.
Are was wondering, like, how, so let's say you're in a chess game,
Right.
and so you're in a state, you take an action, and so you're in different states. But then your opponents take an action on which you have absolutely no power, right?
Yep.
So then which state would you rather take into account? The state that you had like actual power on, or the...
In the, like classically, if you do reinforcement learning in the games, environment and opponent are sort of merged into one. So when you make a move, the next state is actually what happens after the opponent's move. And what happens in between is just like skipped.
So you think like your opponent is like the best opponent, and it makes the move.
That's well, that's a good way to think about it. That's actually up to you, right? You model the environment as like a joint system of the game and the opponent, and then if you apply classical RAL, then you actually you need some algorithm for the opponent. In order to make this black box environment, you need an actual opponent predictor, and you just use like the best algorithm you have, or you self-play. You use the same algorithm that you're training, right? And if you use model-based reinforcement learning, where you actually decide that the transition probabilities, which is like the probability of getting into a certain state after your action, the transition probabilities are somewhat known. Then it also consists of two models, of the game model and the opponent model. And then you need to develop this like transition probabilities for the opponent. So in any scenario, you need an opponent model, and it's either self-play or some algorithm you have. All right, so Alexander asks, the main point is to, it's not, it's to think about reinforcement learning as like in components, and in which components are useful for your task and which components aren't. It's quite, it's quite damaging, I think, that people think about it in terms of these algorithms, because, for example, it's very unclear how, like, if I talk about two algorithms that I compare and you don't know anything about them, then you don't know how similar or different they are. And some of them are literally like one small hyperparameter change away, and others are quite different. And also, we have less tricks than algorithms. So why learn like 20 things if you can learn 10? And there's also this disconnect in libraries. Most reinforcement learning libraries, like all of the ones I showed on the slide, and these are the most popular ones, they think in terms of these algorithms. So you have to pick, do you want A to C, or do you want NAC, or like which one of the options you want, and you'll get this exact hyperparameter set, essentially. And there are some exceptions. Like there is a new library that's pre-released, so it's on Facebook Research's GitHub, and they ask you not to rely on it too much because it's a pre-release, where they completely do away with this algorithms. And they just have components. They have a distribution component, they have a time difference component, they have an on-policy and off-policy component, they have experience replay component, and you just string them together into what you want. So it was nice to see that like me and Facebook Research are on the same page there. And I think that we are probably moving in that direction. But right now, like all of the most code you'll see with the reinforcement learning does like import PPO, and then there are all these papers that will talk about, which is the reason why we have all these weird algorithm names, because they talk about us like inventing the novel algorithm where they actually like added a different clipping. And this means that because of the incentive of publishing papers, the field is slightly obfuscated. And the goal of this work was to de-obfuscate it.
Where is RL used in medical imaging?
I mean, I'm currently trying to develop an agent that will control the movement of the probe in ultrasound. So the job of an ultrasound sonographer, where you need to take a very particular shot of, in my case, it's fetal scans. So it's a pregnant woman, and you need to take a shot, an ultrasound picture of the child that has stomach in the umbilical vein, but doesn't have a heart on the picture. And this sort of the task of positioning the probe in the correct way so that the picture fits all the requirements. And then this is an environment where you have actions like move the probe up, down, left, and right. And your reward is how good the image is. I actually made rewards like I have an image fitness function that's based on clinical guidelines. There's like a clinical paper on what the image should be like. And I just like coded this paper into a formula, right? And then the reward you get for a step is the difference in fitness between the previous image and this image. And so I turned this into a reinforcement learning environment, and now I'm trying to use reinforcement learning to actually train this automatic sonographer. Also, it turns out to be that I'm the second person to do it. There are like some differences between the previous work and my work. They have a very different scenario, not fetal scans. But what's interesting is they actually put this algorithm onto a real robot hand and made the robot hand do the job and take scans.
So the idea, I guess, is that you cannot guess from the initial position the last one, and so you have a kind of trajectory that you want to optimize to get from A to B.
Yeah, you have to learn. Yeah, you have to learn how to take the correct trajectory. We also give a little bit of a negative reward additionally every turn, so that you're incentivized to find the correct image faster. So you essentially you start with a picture where you don't see anything useful, but you usually don't see any of the three organs, heart, umbilical vein, and stomach. And based on this picture, I have to decide like which way you should go, which is quite hard. Yeah, hopefully reinforcement learning can help this problem.
Do you expect the algorithm to actually learn the anatomy without actually learning
it? Yeah. I'm also looking into maybe separating the visual part and the action part. So if someone else have already done the job of training a good model for someone else on ultrasound, for example, some classifier, organ classifier, take this neural network as an image encoder and use it as an observation for the reinforcement learning agent. There are quite a few neural applications in healthcare. Actually, there's a lot of people are trying to turn, like a lot of people are trying, and many of them are really bad at it, but are trying to turn Mimic3 dataset into some reinforcement learning environment. In Mimic3, you have events from ICU. From intensive care, and you have like all kinds of events, right? You have every single drug that was given to the patient, patient's admission and discharge, every single like test that the patient took, and so you can say that
it's not an advance in that case. And those events are non-advanced. So you have them.
Yeah. So you have a data set. You don't have an environment. You have a data set.
Yeah.
I think the scenario where we will be reinforcement learning in healthcare on a live patient will never happen. But you have a data set, but it's still useful to turn it into a reinforcement learning environment, because that will let you optimize for quality and not for imitation. Right? So in this environment, you have observations which are like vital signs, heartbeats, oxidation, various blood pressure parameters, and then you have doctor's actions. So you have observations and actions, and you can use supervised learning to learn how to imitate doctors from that environment. But if you want to optimize not for imitating doctors, but for treating patients, then you might train a different model. You might train a model that predicts what happens after a certain action. But you use supervised learning to train a predictor model based on action and state, predict next state and what goes on to the patient. And then if you want to extract the correct strategy from this model, you have reinforcement learning. And so this model becomes your environment, this predictor of what happens to the patient that you trained on data, it becomes your environment, and you use reinforcement learning to train an agent in this environment. And then you have an agent that was data-driven, that was trained on a clinical data set, but it's not optimized for imitating doctors. It's optimized for optimizing healthcare outcomes. But unfortunately, a lot of these environments are quite bad. So the idea is really great, I think, and it has a lot of potential. But for some reason, I think people who do it are just very good at regularization and modeling and all the issues that happen. Because there is a very well-known environment called GMIC, which is a sepsis simulator trained on Mimic, and it has a panacea basically. There is your action in this environment. Your action is a vector of drugs. So every number in that vector is how much of each drug you give the patient, and there is a magic vector of drugs that helps. Always doesn't have any side effects. It's just the perfect solution for every situation. So you can even throw away the observation and just input the magical sequence of drugs. So they clearly really failed somewhere at training this neural network, and this really highlights the problems and the importance of validation, right? So in order to actually use something like this, you need a very robust approaches to validation of the simulators to basically prove that they're accurate. But I do think that this is all possible. Any other questions, comments, or remarks? Okay, I guess then thank you everyone who showed up. Thank you for persevering through all of the technical issues we had. I had to actually get into this and maybe see you at some later installment, because it happens semi-regularly, once every 2 weeks to a month.
Okay, thanks.
Thank you.